Welcome to GER Mathematics and Statistics lessons. In today's video, we shall continue our discussion on real numbers, okay? And we shall be talking in particular about the irrational number system. Now, please, before we begin, smash a like on this video. If you love our content and you've been following us, smash a like on this video. Thank you very much for your subscriptions. For those who have subscribed to the channel, if you haven't subscribed to the channel yet, please do so by clicking the subscribe button below. Okay, thank you very much for your shares of our videos, your likes to our videos. Thank you for your comments on our videos. We are very grateful from the depths of GER Hub. Okay, so thank you very much for all you have done and have been doing to support this channel to ensure that we grow. We are very grateful. That being said, let us focus our attention on the subject matter: irrational number systems. So the question is, what are irrational numbers? So irrational numbers, I'm going to start with this. The first statement I'm going to make here is that irrational numbers, as the name implies, are numbers that are irrational numbers are numbers that are not rational. Full stop. Now, what does that mean? That brings me to the second statement. Now, if you remember, we used this type of Q to represent the rational number system in our video on rational numbers. So please watch our videos on rational numbers. Okay? Go back and watch our video on rational numbers. So we use this type of Q to represent rational number system. And we had defined the rational number system as a system containing the set of all x, such that x can be written as a over b or expressed as a over b, and b is not equal to 0, where a and b are members of z, the integer number system. So if you want to define the rational numbers or the rational number system, take note, the rational number system is a system containing numbers that can be expressed as a ratio of two integers, such that the denominator must not be 0. Now, if we say that irrational numbers are numbers that are not rational, then it means from this statement, and coupled with what we know about rational numbers, that irrational numbers can be represented also, just like we can represent rational numbers as Q. We can represent irrational numbers with this symbol F. Okay? If we use this symbol F to represent irrational numbers, then we can actually define it in a similar manner to how we defined it using for rational numbers. Okay, so the irrational number system is a system that contains all elements x, such that x cannot be expressed as a ratio of a over b, whether or not b is not equal to 0 and a and b are members of z. So in the rational number system, elements could be expressed as a ratio of a to b or a over b, and b was not equal to 0 and a and b were integers. So a system in which you have a ratio of two integers, where you have, in a system where you cannot express a number as a ratio of two integers, whether or not the denominator is 0, that system is called the irrational number system. Okay? Now, what I want you to know from the onset, I told you on our videos on real numbers that we would save the best story for the last. We have been calling it real numbers, our videos, real numbers, our videos. When we discuss number systems, when we discuss the natural number system, we call that video real numbers. And our focus was to discuss the natural number system. When we call the next video real numbers, our focus was to discuss the integer number system. When we call the next one in the series real numbers, our focus was to discuss rational numbers. Now we are also calling this video real numbers, but our focus is to discuss the irrational number system. Okay? Now, again, that being said, repeat myself, that irrational numbers are numbers that are not rational. Number two, rational numbers, remember, are a system. Rational number represents a system such that every element x can be expressed as a ratio of two integers and the denominator must not be 0. Now, if you use this symbol F, wave F, to represent the set of all x such that x cannot be expressed as a ratio of two integers, then you would come to realize that that system gives rise to a system called the irrational number system. Now, one thing I want you to know is that the union of rational number system with the irrational number system, the union of the rational number system with the irrational number system gives a new system we call the real number system, represented with this type of R. So the real numbers or the real number system are represented with this type of R or this type of R. Okay? So a double stroke R represents the real number system. How do you form the real number system? You unite the rational numbers, the rational number system with the irrational number system. So uniting the rational number system with the irrational number system will give rise to the real number system, denoted by that R. So if you cannot write the real number using this notation, then you can simply write it like this. Okay? Either way, you'll be correct. Now that brings me to the next statement. Okay? Now, what gave rise in mathematical history to the irrational number system was of Greek origin. Okay, it was of Greek origin, in which case the ancient Greek philosophers or Greek mathematicians attempted to actually get the length of the diagonal of a unit square. Now, a unit square, take note, is a square that has all sides of the square as one unit. Now, in ancient Greece, ancient Greek mathematicians or philosophers, whichever one you want to call them, attempted to get the length of the diagonal of a square, a unit square in particular. Now, they got a result x, which ended up giving them square root of 2. Okay? Now take note, if this is a square, then all the vertex, at every vertex of this square, you have a right angle. Okay? Now, in ancient Greece, ancient Greek philosophers or mathematicians attempted to get the length of the diagonal of a unit square, and a unit square is a square that has all sides equal to 1. Now, for them to get the length of the diagonal, they ended up using Pythagoras Theorem. So using Pythagoras Theorem, remember, the adjacent squared plus the opposite squared will give you the hypotenuse squared, right? Now, that means that 1 being the adjacent in this case, plus 1 squared plus 1 squared, that is 1 being the opposite also, will be equal to x all squared. Now, it means that x all squared is equal to 1 squared plus 1 squared, and that can give you x squared equals 1 plus 1, because 1 squared plus 1 squared is 1 plus 1, and that gives you x squared equals 1 plus 1, which is 2, implying when you take the square root that x is equal to the square root of 2. Now, the problem they realized with this result was that the result happened to be one that was not found in the largest system at that time. And at that time, the largest system was the irrational number system, or the rational number system, sorry. So, as at the time they obtained this result, square root of 2, the largest system known to them was the rational number system. So, quickly, looking at the numbers that should be contained in the rational number system, square root of 2 was not found among the numbers in the rational number system. So, attempts were made by the philosophers then and the Greek mathematicians then to see or to prove that x equals square root of 2 was a rational number. But all attempts to prove that x equals square root of 2 was a rational number proved abortive, because they ended up discovering, after all, after several attempts, it was discovered that square root of 2 was not a rational number. So that is what gave rise to that problem, and that is what gave rise in turn to the idea or the number system called the irrational number system. So the first thing we are going to do here before we discuss the irrational number system further is to prove that square root of 2 the actual problem that gave rise to the rational number system is actually not a rational number. So how do we get that done? I'm going to call this a theorem. I'm going to state a theorem here. Now, what theorem am I going to state? I'm going to state the theorem that x equals square root of 2 is not a member of Q. That is, x equals square root of 2 is not a rational number. Now, take note, the proof of this theorem is by contradiction. Okay? The method of proving this theorem is by a method called proof by contradiction. So what do we do in proof by contradiction? If you want to prove that A equals B, and you want to prove that A equals B by contradiction, then you have to start with saying or making the assumption that A is not equal to B. So when you state that, when you attempt to prove that A equals to B by assuming that it is not equal to B, then you are actually going about it as a proof by contradiction. Now, so for that reason, we are going to assume that after all, there exists an x there exists an x that is equal to 2. There exists an x that is equal to square root of 2 in the rational number system. Okay? Now remember, we want to prove that x equals square root of 2 is not a member of the rational number system. But because we are proving by contradiction, we will start with assuming that x equals square root of 2 is actually a member of the natural number system. Now, what that means is that if x equals square root of 2 is a member of the rational number system, then it means that we have to make a recall of the fact that x, any number in the rational number system, can be expressed as a ratio of two integers. So remember that the same x can be expressed as a over b, where b is not equal to 0. Now, if x equals to a over b, and we are assuming that x equals square root of 2 is a member of the rational number system, then it means that what it means is that a over b is actually equal to square root of 2, and that means that a is equal to b times square root of 2 if you make a the subject of formula. Now, at this point in time, we are going to assume here that a and b are not factors. A and b are not factors of each other. And if we make the assumption at this point that a and b are not factors of each other, what does that assumption mean? It means that a and b, a over b, is the simplest form of square root of 2. If actually we can actually express square root of 2 as a ratio of two integers, it means that if we assume that a and b are not factors of each other, then it means that a and b are co-prime. They are co-prime. Okay? So two numbers are co-prime when they are not factors of each other. That is what we mean. Okay? Now, that being said, let us proceed. Okay? So let's proceed. Now, to proceed from this point, let us see. The next thing you are going to notice is this. If you take the square of both sides, take the square of both sides of this equation. Let's call this one equation 1. So take the square of both sides. Take the square of both sides of equation 1. Okay? So if you take the square of both sides of equation 1, you will notice that a squared is equal to b squared times 2. Because squaring both sides means you would have to square b, and you have to square the square root of 2, and the square of the square root of 2 is 2. So it means that a squared will be equal to 2b squared. Okay? Now, what does that mean? It means you should take note of the following. Now I'm going to put this in brackets, some things you need to take note of. Number one, point number one is this. Whenever you multiply an odd number, if you multiply an odd number by 2, so 2 times an odd number will give you an even number. Please take note of that. Number 2, if you square an even number, the result will be an even number. So even number square, even number all squared will give you an even number. And if you square an odd number, that is odd number square, the square of an odd number will give you an odd number. Now, why am I telling you to take note of this? Look at it carefully. Remember, the assumption we made earlier on is that A and B are co-prime, meaning that A and B have nothing in common. And if they have nothing in common, it means that they have no factor in common. And this is the simplest form of expressing square root of 2 if we assume that square root of 2 is actually a rational number. Okay? Remember, we are proving by contradiction. Now, take note of one thing. Now, since you have seen this, that a squared is equal to 2b squared. If a squared is equal to 2b squared, it means that a squared is, after all, an even number. Okay? So, a squared is an even number, and that is why you are having this. Because a squared cannot be odd. Why is it that a squared cannot be odd? It is because 2 times an odd number will give you an even number. So if you multiply b squared, let's assume that b squared is an odd number. 2 times b squared will give you a squared. And a squared, in that sense, becomes an even number. Okay? Now, if a squared, based on that assumption, is an even number, what it means, let's continue from this point. What it means is that if a squared is an even number, it means it is possible to write, it means then a squared, then it means that a itself can be written as 2 times a number, say h, in which case h is a member of n, the natural number system, okay? Or, in particular, you can even make it broad, a is a member of z, or h is a member of z. Now, so what have we done here? A squared is equal to 2b squared means that a squared is, after all, an even number, because 2 times an odd number will give you an even number, and the square of an even number is an even number. So it means that a is an even number. So if we want to show that indeed a is an even number, so we can write a as 2 times h, where h is an integer. Now, if we call this expression here, if we call this equation 2, call this equation 2, let us substitute for a equals 2h in equation 2. If you substitute for a equals 2h in equation 2, then what happens is that you are going to end up having, wherever you find a in equation 2, what are we going to put? We are going to put there 2h. So this one becomes 2h squared equals 2b squared. Now, if you expand 2h squared, you end up having 4h squared equals 2b squared. Now, if you make b squared the subject of formula, you end up having 2h squared. Okay? Now, what does that tell you about b also? It tells you, because you can express b squared as 2h squared, it means also that b squared is even. Okay? It means that b squared is even. Now, note one thing. We earlier stated that a over b equals square root of 2 is the simplest form, meaning that a and b have nothing in common. But what we are beginning to see is that, after all, since a squared is equal to 2b squared and b squared is equal to 2h squared, you will notice that a squared over b squared is the same as 2b squared all over 2h squared. And that tells you that a squared and b squared, or a over b all squared, implies that this implies that you have a squared and b squared giving you 2b squared over 2a squared, this tells you that a and b are not, it tells you, because you have a squared equals 2b squared and b squared equals 2a squared, it tells you that, contrary to the assumption we made, a and b are not co-prime. Okay? And if a and b are not co-prime, it means a over b is not equal to square root of 2. and it is therefore not a member of the rational system. Okay? And that proves that square root of 2 is not a member of the rational system. Okay? So, that being said, let us quickly go over what we have said so far about the rational number system. The irrational number system. Now, the irrational number system is a number system that contains numbers that are not rational. That's number one. Number two, remember that rational numbers are numbers that can be expressed as a ratio of two integers. Now, if irrational number system contains numbers that are not rational, it means that irrational numbers are numbers that cannot be expressed as a ratio of a over b, and in which case b is not equal to 0. Now, what it means is that the rational number system has nothing in common with the irrational number system. So, uniting the rational number system with the irrational number system will give you what is called the real number system. So, real numbers are made up of two systems in union, and that is, the systems are the rational number system and the irrational number system. Now, the next thing I have said in this video is geometrically, what gave rise to the problem of irrational numbers is this problem of finding or trying to obtain the length of the diagonal of a unit square. And that was the problem in ancient Greece, where mathematicians at that time, Greek mathematicians or philosophers, attempted to get the length of the diagonal of a unit square. What did they do? They applied Pythagoras Theorem to the unit square, the size of the unit square, taking note of the fact that the unit square is a square that has all sides equal to 1. Now, using Pythagoras Theorem gave them x equals square root of 2. But as at that time, the largest number system known was the rational number system. But looking at the rational number system, they discovered that all attempts to verify that square root of 2 was a rational number proved abortive. So they started developing proofs to show that the square root of 2 is after all not a rational number. Now, what proof did they give to that? They started with proving that x equals square root of 2 is not a member of the rational number system. But to prove that, they had to use contradiction. That proof was done by contradiction. So the proof started with showing that x is equal to square root of 2. And take note, if a number is a number such as square root of 2 is x and a member of the rational number system, it means it can be expressed as a over b. So saying that x equals square root of 2 is a rational number means that square root of 2 can be expressed as a ratio of two integers. Now take note, the assumption here is that a over b is the simplest form for expressing square root of 2. And if a over b is the simplest form of expressing square root of 2, it means that a and b have nothing in common. And that means that they are co-prime. But if you look at it critically by making a the subject of formula, a will give you b equals b times square root of 2. And I call that equation 1. If you take the square of both sides, you end up having that a squared is equal to 2b squared. And I call that equation 2. Now, the square of an even number gives an even number. And whenever you multiply an odd number by 2, it ends up giving you an even number. But we had earlier assumed that these numbers were co-prime, most likely implying that both of them may be odd, or one could be odd and the other one could be even. Now, the square of a gives you 2b squared, telling us because 2b squared is what you have there, b squared is being multiplied by 2, tells you that a squared is even. And if a is even, it means we can write a as 2 times h, where h is a number that is a member of that's where h is an integer. And if h is an integer and we can write a as 2h, putting 2h in place of a in this equation 2 gives you 2h squared equals 2b squared. And if you expand that, that will give you 4h squared on this side and give you 2b squared on this other side. Now, if you simplify by making b squared the subject of formula, you end up having that b squared is equal to 2h squared, which also implies that b squared is even. Okay? Now, if b squared is even, what it means, if b squared is even, it then means that a squared equals 2b squared and b squared equals 2a squared. After all, a and b have something in common. So, if a and b have a factor in common, it contradicts what we said earlier on. And that means that a over b is not equal to square root of 2 and it's not a member of the rational number system. Now the last thing I want to tell you to round up this video on rational numbers is this. So rational numbers, just like irrational numbers, can be identified or can be put in decimal form. Now, decimal form of irrational numbers. Okay, so just like rational numbers, we can put this irrational numbers in decimal form. So if you have an irrational number x, you can write it as a0, a1, a2, a3, a4, and so on. Take note, if a number is irrational, the kind of decimal it produces will tell you truly that it is irrational. When a number is irrational, in decimal form, it has what we call non-repeating, non-terminating decimals. So one quality of an irrational number is that an irrational number would always produce non-repeating, non-terminating decimals. You take note. Whereas rational numbers will produce recurring decimals or finite decimals. So a typical example of an irrational number may be a decimal like this: 24.32358769334, and so on. Notice that there is no pattern to this decimal, and this may be a clue that the decimal must have come from an irrational number. Okay, so one way to identify irrational numbers is by putting them in decimal form, because in decimal form, irrational numbers are non-terminating decimals. Non-terminating in the sense that the decimal keeps going on without any pattern. Okay, now you must take note of some examples of irrational numbers. Examples of irrational numbers. Some examples of irrational numbers are square root of 2, which gives you 1.4142136 ... and so on. Another example you could look at is e, the number e, called the exponential, 2.7182845945 ... You see it? So this number is also an irrational number. You can even look at pi, which is 3.14159265 ... And it is for this reason the closest number to pi is 22/7. Okay, so pi is not 22/7. Please take note. If you have been telling people or going around saying pi is 22/7, take note, pi is not 22/7. Pi is not 22/7. The closest number to pi is 22/7. That is why you would always see any problem involving pi, you will be given pi by they will be telling you take pi to be 22/7. Okay, so pi is not 22/7. The closest number to pi, which approximates pi, is 22/7. That being said, thank you very much for watching this video. Thank you very much for subscribing to our channel. If you have not subscribed yet, please make sure you subscribe by smashing the subscribe button. Click the subscribe button, smash the like button. Thank you very much.